Hello everybody, my name is Tanner and I'm going to tell you about RAELLA, our paper on efficient, high accuracy processing and memory. So to get started, conventional deep neural network or DNN accelerators fetch inputs and weights from memory. They compute with these and then write the results back to memory. However, this data movement to and from memory can consume a significant amount of energy. As a solution, processing and memory accelerators move computation inside memory using analog processing. This allows them to avoid movement of the data-intensive DNN weights. The pie chart on the left shows the energy breakdown of a processing and memory accelerator. Analog processing can be very efficient, but because it's analog and most chips these days are digital, we'll need a digital to analog converter to convert our digital inputs to the analog domain for processing. Likewise, we'll read out our outputs with an analog digital converter, or ADC. ADCs can consume a significant amount of energy, so to achieve efficient processing memory, we'd like to reduce this ADC energy. This plot shows DNN accuracy on the x-axis and accelerator energy on the y-axis. Accelerators that pay a lot for the ADC are at this dot in the top right, where they're inefficient. We'd like to move to the star by reducing the ADC energy. One way to do this is by reducing the range of the ADC, which reduces energy. However, because the reduced range ADC can no longer represent all the values the DNN needs, we also lose accuracy. Many works recover this accuracy by modifying and retraining DNNs. However, this whole route can be problematic, because modifying and retraining DNNs can be difficult and expensive. As an alternative, RAELLA takes a shortcut. We'd like to reform computation such that a large ADC range is not needed in the first place. So how do we do that? Well, our analog domain computations will produce some distributions of analog values, which nominally require a large ADC range to represent. To reduce this range, first notice that each of the distributions has a different mean. We'll pull out this mean and represent each distribution only by a small difference. This will shift the mean of each distribution into the center of the ADC range, shrinking the overall required range. However, we're still limited because computation B requires a larger range than the other two. What we can do here is break up or slice the computation into smaller pieces. When we do this, each of the pieces of the computation will produce smaller results, ending up in a smaller ADC range. However, we're still limited because there are outliers. These outliers create long tails in the distributions that require a larger ADC range to represent. We deal with outliers by speculating that values will end up in a more narrow ADC range and recovering out-of-range results. Because outliers are infrequent, recovery is rare and high efficiency. These three strategies allow RAELLA to improve energy efficiency by up to 5 times and throughput by up to 3 times over prior works. They also operate with little to no DNN accuracy loss and are no retraining required. They can run off-the-shelf DNNs without modification. If you'd like to hear more, we would love to see you at the full talk. Thank you.